Started. Our next speaker is Yian Ma. He's an assistant professor at the Halisoglu Data Science Institute at University of California, San Diego. Before that, he was at Google Research, and then before that, a postdoc here in Berkeley. He got his PhD at University of Washington.
Oh, yeah.
He's an expert on many aspects of machine learning, with particular emphasis on Bayesian inference in high dimension. And today's talk is about the convergence of Langevin and when is it dimension independent.
All right. Thank you, Santosh. Thank you so much for the generous introduction. And I want to thank all the organizers of the workshop for pulling this off. It's been trying time. Today I want to talk about a problem that I've been started thinking about during my time at Berkeley. And it's partially motivated by Santosh's talk back then. And that is, when is the convergence of the Langevin algorithm dimension independent? So the previous work with Wenlong was actually along this line of thinking. We were trying to improve the dimension dependence of the convergence time of the Langevin algorithms. And in this talk, I'm going to take a composite optimization viewpoint so that we make the convergence rates tight so that we can understand when is the dimension dependence not necessary. Okay, but before I start, I would like to first acknowledge my amazing collaborators, Tong Zhang from Google Research and Yoav Freund from UCSD. So this whole program is called Geometric Methods for Optimization and Sampling. So this work is really motivated by this whole line of research we have all been doing on drawing a parallel between sampling and optimization. In particular, we're trying to establish non-asymptotic convergence rates, borrowing ideas from optimization and all sorts of different fields. So Andre was here. So he was, one of the first people to establish that Langevin algorithm has this parallel with gradient descent. At least in the continuous limit, you can think of it as a gradient flow over the KL divergence when we define the space to take the W2 metric. But there is a conspicuous distinction between optimization and sampling. That is, optimization doesn't have this dimension dependence whenever you have convexity, right? But sampling does, and it's been bugging me for a long time. So this motivates the question we've been asking during the start of the talk: when is the Langevin algorithm's convergence time dimension independent? So to address this question for strongly convex and Lipschitz smooth problems on RD, Intai would say that this dimension dependence is in the diameter of the problem, so it goes with epsilon, right? Whenever you have a accuracy dependent, you have a dimension dependent. And Roche is in the audience; she might also agree. But I would say that this is a compelling argument, and in the worst case, it may very well be true. But beyond the worst case, things can be different in the sense that if we think about the ridge separable case that Wenlong just introduced, and if we further assume that each individual log likelihood is Lipschitz smooth, then there is a way to smartly initialize so that the initial error actually doesn't depend on the dimension. So it gives us some hope that things may become dimension independent under some of those cases, right? So this is when I started this discussion with Tong Zhang, when he asked, "Are you sure that the convergence rates for the Langevin algorithms are tight?" I wasn't sure, and I just said, "Well, it's a developing field. We got a lot of help from optimization experts." Then he said, "I feel that optimization methods can help more." Basically, he said, "Well, at least for stochastic gradient methods, for SGLD, it should correspond better to SGD method." I didn't know what he meant, but I started working with him on this class of MCMC problems, where we had this posterior distribution of the parameter theta depending on the data, which is proportional to e to the negative potential function. And we'll just note it as P star as the target distribution. And then it's comprised of a likelihood function. So we can write it as proportional to e to the negative temperature inverse times f function, where temperature is defined by 1 over the number of data points. So then this function becomes the empirical risk corresponding to optimization literature. And this prior is negative temperature, negative 1 over temperature times this regularizer. And this regularizer is oftentimes simple and tractable, so that we can do all sorts of maneuvering with it. And the hard part is this empirical risk. So we mark this with a red color and mark the regularizer as a blue color so that it's benign. And in this case, the outline of the talk will be, we'll first describe some of the previous approaches, and we'll describe a composite optimization approach. And then we'll consider two cases. One is that this f function, coming from the likelihood, is convex and Lipschitz continuous. And then this g function is strongly convex. And another case corresponds better to the previous talks, which is f plus g function is strongly convex and Lipschitz smooth. Okay, let's start with some of the previous approaches. This will just be a review for all of us. So in this approach, we would usually discretize the Langevin dynamics, which preserves the posterior distribution, so that the continuous dynamics is just gradient flow plus the Brownian motion. And it's equivalent to the vector field, so that we take at every point following this current P distribution. This is the negative gradient of KO divergence when we define the metric to be the Woz times 2 metric. And this implies linear convergence whenever we have, say, strong convexity or log-Sobolev inequality. So this is all well and good. The problem happens when we discretize it. So after discretization, this is the gradient descent plus a Gaussian random variable. So it's equivalent, just like Wenlong talked about, to plugging in this previous iterate into this gradient of u, and then integrate everything, treat it as a constant, right? So this is equivalent to taking at time t a sort of modified gradient, right? Where on the upper side, we have gradient of log pt taken over at theta t. But on the bottom side, we have gradient of log p star taken at the previous iterate. It's like the gradient is evaluated at different points. It's like we have two paths. One path tells you that you should follow this windy, curvy path and integrate it explicitly. Another, the animation takes a while. So another is telling you that you just put in a initial point, compute the gradient, follow this straight line, and go there, right? Of course, there's going to be discrepancy, and this discrepancy can oftentimes be described as expectation of norm squared of this difference. And so note that theta t minus theta k comes from this difference in this normal random variable, right? So the variance of this normal random variable scales with dimension d. So that's why we always get this dimension dependence. So at this point, a lot of optimization experts would ask me, why don't you skip the continuous part? Just do the discrete time, just take the discrete time perspective. Right, why do you always go into this trouble and then you have this dimension dependence? So there is one work that previously tried to address this. This is by Alan Dervis and his collaborators. What the approach they took was the following. So they would decompose the KL divergence into two parts. One is the self-entropy. Another is the cross-entropy. Right? We overuse this U to denote this functional over the distribution of P. So they took this composite optimization viewpoint so that you can decompose the KL divergence and also decompose this Langevin algorithm into two parts. One part is the gradient descent part, and it can also be proven to be the gradient descent over this cross entropy. Another part is this Gaussian random variable part, can be proven to be the gradient flow over the self-entropy, right? And then, so if let's say U is strongly convex and Lipschitz smooth, you have the classical result from optimization, right? So because the left-hand side is bigger than or equal to 0, so you have this exponential convergence if you do the iterate. And this H function, this self-entropy, because you have geodesic convexity, you also have something the same as in optimization literature. And this gives you 1/t convergence if you take a telescoping sum, right? So on their own, they're all very good. The problem is that they don't go together very well because they are centered at different points. So when you combine them, inevitably there's this discrepancy. So if you add in and subtract a function that's u pk plus 1 minus u pk tilde, that goes back. That's also the discrepancy before and after adding this Brownian motion, adding this Gaussian random variable. And due to the variance of this Gaussian random variable, you still get a dimension d. Right. So Tong and I have been staring at it for a while. And then Tong says, why don't you align the updates differently? So previously, you decompose this update into these two steps. One decreases cross entropy, one decreases self entropy. You can write it out. And instead of focusing on this block, you would focus on the blocks before. So it's like you first add a Gaussian random variable, and then you plug into gradient descent. If you do that, the analysis can go a little differently. So let's put it up there. And geodesic convexity of H is the same. So the update in the self-entropy is exactly the same. What's different is that let's look at the intuition and forget about the setting for a moment. Let's just assume U is convex. Then in this case, so the difference in U is now aligned with this self-entropy, and then the other part is also classical in convex analysis, right? So now you can readily combine these two, so that self-entropy plus cross-entropy gives you KL divergence, and then have this update rule. And so, like for people familiar with convex analysis, this directly gives you that if, say, U is Lipschitz continuous, this one is bounded, then adaptive step size of 1/√k lead to 1/√k convergence rate. The problem, of course, is there's this initial condition dependence, which depends in turn on the dimension, right? So now let's look at the setting that we talked about. That's when we have a convex and Lipschitz continuous f and a strongly convex function g, what would happen? So to remind people, f corresponds to the likelihood and can be complicated. G corresponds to the prior, can be simple. So in this case, we have three terms in the KL divergence. We have a G term, and F term. And now, instead of grouping G and F together, we would group G and the self-entropy together so that it's a regularized entropy. And we denote it using the blue color HP so that the color corresponds to G. And we have this cross entropy term, which we denote by FP. So in this case, instead of so because we're putting G together with the Brownian motion, we sort of directly integrate it so that it would decrease this regularized entropy instead of the self-entropy. And then so the gradient descent over F is the same. It decreases the cross entropy. So a few more words about the first line of the update. So for G being a Gaussian distribution, we already have an explicit result to solve it. And for Bayesian elastic net, kind of like L1 plus L2 regularizer, we also have an explicit kind of form of expression. And we can solve it efficiently for sort of coordinate-wise decomposable G, right? Because that would be like a constant times number of gradient evaluations. So under this setting, we can sort of solve pretty easily that we now have a strong geodesic convexity of this regularized entropy. So we'll have this exponential convergence now if we only look at the convergence in this regularized entropy. And now for the convexity of F, we have the same thing as before. And if we further assume it's G Lipschitz continuous, then this is a constant, and we can take a step size which matches these two, so that we can combine them to get a convergence for KL divergence, right? And by taking this step size h to be 1 over scale like 1 over mk, then we get the classical optimization result that is sort of g squared over m over beta m, and beta is 1 over m. So here the best initial step size we can take is infinity, because when we take it, then we integrate it towards the stationary distribution. So it's same as initializing from this prior distribution, right? So when we do that, we get that the KL divergence scales like g over beta m times k. And it translates using Telegram inequality into what is time to distance to g squared over m squared. So this is an interesting result, but it's difficult to compare to the previous results, right? Because we assume there's this splitting, and one is Lipschitz continuous. Can
you ask you? Sorry, please remind me about what is G and the M strong geodesic convexity also. Yeah.
Yes, M is the strong geodesic convexity.
And by that you mean?
I mean that this function G is M strongly convex. Yeah, so because it's like the regularized entropy. And F is F is G Lipschitz continuous. Oh, sorry, I was going a little too fast, I guess. Any questions? Okay, so let's maybe let's look at something that can relate better to previous results. So if we look at the case where F plus G is strongly convex and Lipschitz smooth, this will correspond better to the existing results. So yeah, as a reminder that F corresponds to likelihood, G corresponds to the prior. So in this case, for the posterior distribution, proportional to e to the negative potential, for the U function potential function being beta inverse M strongly convex and beta inverse L Lipschitz smooth, we can directly take G to be M over 2 theta norm squared, this normal prior, because F is equal to beta U minus G is just convex and Lipschitz smooth. Right? We can directly do this splitting. So in this case, this first line of update rule can be further simplified to be sort of explicit, like the following, right? It's just this normal distribution. And in this case, we have exactly the same thing for sort of going from strong geodesic convexity of this regularized entropy, and then we also have from convexity of F this expression. And now, because we are no longer assuming that F is Lipschitz continuous, but instead Lipschitz smooth, we cannot just get rid of this term. So instead, the difficulty becomes to bounding this term. And to bound this term, we can separate it into two terms. One is the difference between this gradient F taken at theta k and the gradient F taken at theta where theta follows the stationary distribution. And then what's left is theta following the stationary distribution of gradient F theta, right? So this is entirely the property of this target distribution we want to sample from. And for first term, we can use geodesic convexity of this regularized entropy and Lipschitz smoothness of F to achieve that this is upper bounded by L times the difference in the KL divergence. Because there is so originally there is a hk squared here. So putting on top of it, we can just absorb it into the left-hand side term, which has this KL divergence bound. Right. So now everything turns into this bound. That's entirely a property of the stationary distribution. Everything else, you can use convex analysis to solve it. Right. Now, so the question is, when is this term dimension independent or dependent? So assume that this Hessian of this empirical risk is upper bounded by a matrix. Then the strong log concavity of P star would imply that this term is upper bounded by trace of this Hessian upper bound squared. And so if in the rich separable case that Wenlong just talked about, which is activation functions over in a product of theta or parameter times the data points. In those cases, assuming that the second derivative of the activation function is bounded, assuming that the data distributes in a bounded region, then the Lipschitz smoothness of each individual log likelihood is Ls times Rz. In this case, we can find that the Hessian upper bound on the Hessian can be represented as 1 over n times Ls sum over this ZZ transpose. And the trace of the Hessian square is upper bounded by Ls squared times Rz squared. Right. So under this kind of individual log likelihood, individual smoothness of log likelihood, we can achieve that. So this is stronger than previous works. Under the stronger assumption, we can obtain an upper bound on the expectation of this gradient f with respect to the stationary measure, which does not have a dimension dependence in it. And in this case, we can sort of plug into our previous iterative inequality, so that we can achieve that the scale divergence is sort of upper bounded by this sort of L squared R squared over M squared. And then here there's this sort of initial condition. And because we have this 1 minus L times H term, we can no longer take H to H0 to be infinity. So we do have this initial condition dependence. And the best we can take for H0 is 1 over L. So I'll talk about sort of an upper bound on the initial condition as we promised at the beginning of the talk. So if we use the sort of intuition from this Lipschitz continuous case, then we know that we should take the initial condition as the prior distribution. Right? So if we do that, then we can use the Talleyrand inequality to first upper bound this Wallerstein-2 distance by the KL divergence, and then we can use the log-Sobolev inequality to upper bound the KL divergence by this gradient difference. Right? And because P star contains G, F and G, and P tilde theta contains G, so the difference only contains gradient of F. And canceling all those beta terms, we see that this directly falls back into our bound on this at the stationary. Right, so this directly implies a bound on the initial condition. That's L squared R squared over M to the cube. Right. So plug that back into our bound. That gives us sort of L squared R squared over M squared squared, but divided by K squared. So it matches this term, which is L squared R squared over M squared. Right, so that tells us that taking K to be sort of L squared R squared over M squared, 1 over epsilon, gives our sort of desired accuracy. And for SGOD, so the first term is the same. We get an additional term, which depends on the stochastic gradient variance in the activation function at the mode. And then this S is the mini batch size. So if, say, this B square is not too large, if, say, it scales like the smoothness of this activation function, then we can actually set the mini batch size to be n over sort of L squared R squared over M squared, or L R over M, so that we can shave off a condition number dependence. Okay, so yeah, so that's the this is a result for the stochastic gradient version of it. And so for the future directions, of course, one question is there a larger class of problems which has no dimension independence, right? And also, can this approach be combined with accelerated methods in optimization or higher order integration methods in MCMC? So that, for this class of strongly convex Lipschitz smooth problems, I think the tight convergence rate should be kappa times log of 1 over epsilon. So the question is, can we combine this approach with previous works to achieve something like kappa times 1 over epsilon to the 1 over alpha's power, where alpha can be arbitrarily large? And with that, I think I'll just thank you for your attention.
Hi, and this is a very interesting talk, very interesting work. And actually, I was just asking Andrea today over lunch about the following question, and it seems like it's I should have also asked you because I'll ask you now. So in the second setup that you looked at, like when you have smooth and strongly convex, do you really need both parts to be smooth and strongly convex? Because it seems like your thing should also work when F is smooth and G is strongly convex, but neither of them has to be both.
Yeah, it doesn't have to. So in the first setting, actually, F is not smooth. F is only.
Yeah, that's why it seems like your whole thing should just work if you have a smooth loss strongly convex regularizer. And the reason you would do that even in the L2 setting is because then you can do the elastic net regularizer, which will not be smooth, but it will be strongly convex, and you can have a smooth loss.
Yeah. We're actually able to do that for the Bayesian elastic net.
Yeah, very cool.
Yeah,
Yeah,
sorry,
so
maybe I went a little too fast.
Oh, thanks.
Yeah, very nice result and very nice talk. I'm wondering, are you familiar with this work by Heyer, like Vollmer, Stewart, like 2014, where they prove like Major's spectral gap in infinite dimension, then it's dimension independent. Like if you're familiar, can you talk about the type of assumptions they assume and compare a little bit? Or
I was hoping you can tell me.
it's an algorithm called like preconditioned Crank-Nicholson.
Oh.
They also assume this composite form like F plus G, where G is exactly Gaussian, they know. And then, yeah, they put some assumptions on F to get the result. But
yeah, if you can send me.
we can talk.
Yeah, we can talk later. Thanks.
Thanks for the talk. We know that in optimization, this individual smooth Lipschitz smooth conditions usually enables the use of variance reduction algorithms. Is it possible to like extend your results in the stochastic gradient case and get better variance reduction algorithms?
Yeah, we think so. Yeah, because this the reason we use this individual log sort of individual smoothness for log likelihood is because we want to do stochastic gradient variance of it. And yes, to do variance reduction also requires this.
So what's the dependence on the tolerance? Like when you show the KL divergence is less than or equal to epsilon, is it 1 over epsilon?
Oh, the epsilon dependence, yes.
Yes.
It's one. Let's see. So if we read this, yeah, it's 1 over epsilon.
Oh, sorry. I mean the first case when F is non-smooth.
Oh, I think
is it also 1 over epsilon?
Epsilon? Yeah. Yeah, it's also 1 over epsilon.
Okay, I see. Do you think this can be improved to like log of 1 over epsilon because you actually have a strong convexity in this setting?
Yeah, that was the question I asked at last, because I feel like this this dependence should be kappa linear in kappa and log in 1 over epsilon.
For the kappa case, this is the smooth, right?
Smoothness,
F is
yes.
smooth.
Yeah.
for non-smooth, do you have a guess on the lower bound?
Smooth, I don't have a guess. I guess if you draw a parallel, it's G over M, but I'm not sure about that.
Well, my guess is like you use G, right? It's like a G square over
G squared
little
over
m
M squared. Yeah.
and the
Also-
log of
Yeah.
1 over epsilon.
Yeah, it also depends on the distance you're talking about in the non-smooth case. Because in the non-smooth case, for KL divergence, so yeah, in the non-smooth case, there is a scaling difference in KL divergence and W2 distance. So in W2 distance, currently it's G squared over M squared. Maybe it can be improved. I'm not sure, because yeah, in previous works, I don't see anything beyond that.
Yeah, in optimization, like for example, subgradient or bundle method, you can show G square over M epsilon. Yes, epsilon is not in the log, but in sampling, I think there are two kinds of tolerance. One is from optimization, the other is for sampling. The epsilon, I mean, I'm talking about for the sampling part. My guess is this part should go into a log, and in the denominator, there may be another tolerance, let's call it delta. This delta may be the one for optimization. Yeah, that's my guess.
Yeah, that is. Yeah.
Like, for example, in the work by Intai Li, Rotishan, and also Kevin Tian, they have an alternating sampling framework. In that work, the sampling tolerance, the epsilon, goes into the log.
Yeah, yeah, that is my guess. That ultimately we might be able to achieve that. Yeah.
Thank you very much.
Thanks. Thank you.